Okay, so we're going to pick up here with part 2. I know I already posted the introduction, and I'm sure I'm going to go over some of this a little bit more, but there's some things that I want to really kind of hit hard on. State functions in particular. When you're talking about a state function, the takeaway is that it doesn't matter from A to B how you get there. What matters is that you start at A and you wind up at B. So for example, from your home to campus, no matter where that home is, I'm sure you can think of 12 different routes to take to get there, okay? Some are going to be the quickest, some are going to be the longest, some are going to be the least traffic, some are going to go through back roads. In the end, it doesn't matter. You go from a house to a campus. So if you look at this little mountain here, these guys are kind of traveling all the way up here. It seems like a much easier trail than these guys over here that are going up this very super steep incline. In the end, it doesn't matter. Everybody gets from the bottom to the top. How they get there is a different pathway. Anything that it doesn't matter how you get from one to the other is a state function. So energy diagrams, it's just a graphic way of showing energy flow. Let me shift this up. There we go. I'll shift that there for right now. If you look at this particular example here, going from solid elemental carbon to gaseous elemental oxygen to get carbon dioxide, what's really happening? Well, these reactants are lowering their energy when they form carbon dioxide. What that means is that it is more energetically favorable to form CO2 than it is to be their individual elements. So if you have a reactant that has a lower internal energy than the products, the change will be positive. So if your reactants have lower energy than the final product, it's going to be a positive delta E. If you have reactants that have a higher energy than the final products, then your delta E is going to be negative. So what does this mean? If we have a positive delta E, then the energy is going from the surroundings into the system. Okay, let me move me out of the way again. Uh-oh. And I'll make me smaller. Or maybe put me down here. Okay. All right. When you have a negative delta E, what that means is energy is flowing out of the system into the surroundings. Remember, we have the system, we have the surroundings, and then we have the universe. So if delta E, the system, is negative, energy is going from the system into the surroundings. If delta E is positive, the energy is flowing from the surroundings into the system. Okay? We care about this because of this relationship here, where Q is heat or energy, W is work. Q and W are not state functions. It does matter how it gets from A to B. So their value, it all depends on the process. What is happening? Is it, is the system giving off heat or accepting heat? Which one of these things is happening? And that's going to change for every problem. So this table is your new best friend. I highly recommend printing this out, like go to the slide, print it out, or just Heck, write it down in your notes. Like just pause this, copy it down in your notes. So when we talk about Q or heat, energy, heat is energy. And when Q is positive, that means the system is gaining energy. That means heat is going from the surroundings into the system. If it's negative, it's losing thermal energy or heat. Okay, so that means it's going from the system into the surroundings. W, work. When it's positive, work is being done on the system. So it's being done on the system by the surroundings. Okay, when work is negative, work is being done by the system onto the surroundings. So if both of these happen to be positive, then your delta E will be positive. If both of these happen to be negative, then delta E will be negative. So heat is the exchange of thermal energy between the heat and the surroundings. Temperature is the measure of that thermal energy. So a lot of times, like recently, I'm sure you've been walking outside and going, oh my gosh, it is so hot outside. It is crazy hot. We don't really mean thermal energy. We're really talking about the temperature, right? But the temperature is just a measure of that thermal energy. It is not the energy. So one of the ways that we can talk about the heat involved and what's happening is with heat capacity. And that's our relationship. By the way, we're going to have a huge number of equations in this chapter. They're most, I want to say 95% of them are on that TRO sheet. So I would just start making, from the PowerPoints, I would just start making a list of all of the equations that each PowerPoint goes through. So heat capacity, capital C, it's just, well, first of all, it's a constant, but it's specific to different systems. So it is a constant, but it's not like the speed of light constant or Planck's constant, or it's the same across the board. It will change per system that we're talking about or per reaction that we're talking about. You will mostly see the units as joules per degree Celsius or joules per Kelvin. So when we look at what's going on here, we have to take into account the heat capacity, basically how much heat will a system absorb, and the change in temperature that's occurring. The larger the heat capacity of the object, the smaller the temperature rise. And that should make sense, because if something can hold way more heat than something else, then the temperature change isn't going to be as significant, because most of that heat is being absorbed by the system. So it all depends on the amount of matter. So 200 grams of water requires twice as much heat to raise to temperature by 1 degree Celsius as does 100 grams of water. So generically speaking, we say 1 degree, raising something 1 degree, 1 gram by 1 degree is a certain amount per compound. And so it should make sense that, it would take twice as much heat to raise the temperature of 200 grams of water rather than 100 grams of water. It also depends on the type of material. Where's my example? Here, sand versus water. Okay, 1,000 joules of heat energy will raise the temperature of 100 grams of sand 12 degrees, but raise water by only 2.4 degrees Celsius. How many times you go to the beach and it's warm outside, 85, 90 degrees, something like that, perfect beach day, and you get on the sand and that sand is blazing hot. There are times they tell you, it literally can cause burns on the bottom of your feet. And that's because sand can absorb heat much easier than water can. So the takeaway here is that heat capacity is proportional to the mass and the specific heat of whatever the material is, whatever compound it is. So with specific heat, specifically, we're going to use Q equals the mass times the specific heat of that item times the change in temperature. Okay, so everything has a heat capacity, and that heat capacity, along with the mass and the change of temperature, will affect the specific heat of that thing. Okay, so note, we've used Q now twice to represent heat. So let's look at this example. If you find a penny minted before 1982, when the pennies were made of nearly pure copper in the snow, how much heat is absorbed by the penny as it warms from the temperature of the snow, which is -8 degrees Celsius, to the temperature of your body, 37 degrees Celsius. Assume the penny is pure copper and has a mass of 310. Now, we're going to look at two things here. Here's copper, 0.385. Was that in joules? Yes, it was. Sometimes you'll see these specific heats in calories, which is just another unit for energy. Okay, so that's its specific heat. Now, always take the time to draw your chart. First of all, I will always give you boiling and melting points. The only thing you have to memorize for is water, 0 degrees Celsius, 100 degrees Celsius. So first, you're gonna, I don't know what copper is. Hold on. Does it tell me here? Let me just Google that really quick. Okay. Final freezing point. Oh, wow, that's a really big number. Okay. So it's 1084 degrees Celsius, and its melting point, let's look that up. Not melting, boiling, sorry. Its boiling point is 2595 degrees Celsius. Now, in this particular problem, the copper penny is going from minus, oops, I need my eraser now. I need to just move these around a little bit. Okay, so -8 degrees Celsius, and it's heating up to 37 degrees Celsius. Okay, so we just have one change here. That's going to be the change. But I want to talk about something else first. Let's just talk generically about water and the two equations that we're using here. We already said water was 0 degrees Celsius. Its boiling point is 100 degrees Celsius. Let's just say I said water was going to go from -10 degrees Celsius to 120 degrees Celsius. That was going to be the range, okay? So what I'm going to do is I'm going to make my little stair step, my heating curve. It's not really a curve, but we call it a heating curve, even though it's more of a stair step. So first and foremost, I got to heat the water up to, or the ice in this case, up to its melting point. And that's going to be a certain amount of energy needed. Then I'm actually going to melt it. Then I'm going to heat it up, heat it up, heat it up some more. Then I'm going to vaporize it. Then I'm going to heat it up to my final temperature of 120 degrees Celsius. So we have 1, 2, 3, 4, 5 steps in this particular example that all require a certain amount of energy. When we're heating up, that's going to be one equation. When we're vaporizing, melting and vaporizing, that is a second equation. Okay, so the second equation is Q equals the specific heat times the mass. The first equation is Q equals the mass times the specific heat times the change in temperature. Okay, so when I look at this and I compare it to the copper one, we only have a heating up, so we're only going to use A. But in my other water example, we have to use both equations. So for step 1, we would use Q equals M times the specific heat times the change in temperature. Then we would go ahead and calculate, and this would give us a number. Then for step 2, we would use B, the mass times the specific heat, and that's going to give us some number. For step 3 of this, same, go back to equation A. And that's going to give us some number, et cetera, et cetera, et cetera. We're going to do that all the way through the 5 steps. In the end, we're going to add them all together to get a total energy needed. Okay. Now, in the copper example, we don't have to do all of these because we only have the one step. There's only a heating up. So we're going to say Q is equal to the mass given times the specific heat, which we just looked up on the chart, and then the change of temperature. Let's see here. All that matters is the net change in temperature. So final minus initial. Don't worry about having positive and negative values. In chemistry, the positive and negative indicate to us direction. If the overall temperature change is negative, that means it's cooling down. If the overall temperature change is positive, that means it's heating up. So the overall temperature change, delta T, is 45 degrees Celsius. Okay. Now when I just do the math and I multiply all of them together, oh, not plus, multiply, 0.385. I get Q is equal to 55.0935 joules, because grams and degrees Celsius has canceled. And my proper sig figs should be 2, because the negative 8.0 limits me to 2 sig figs. So it's just going to be 55 joules. And that's how we solve these. Okay, so when we transfer and we have something hot added to something cold, the final temperature of both will be the same. And so the final temperature is the final temperature once all the heat is transferred. So if I have a hot piece of metal and I put it in room temperature or cool water, then the Q of the metal is going to equal negative Q of the water. So Q of the metal would just be the mass of the metal times the specific heat of the metal times the change in temperature of the metal, and that's going to be equal to the negative of the mass of the water times the specific heat of the water times the change in temperature of the water. So what I like to do is I like to say, just rearrange this because it just makes it easier to solve. Q of the metal plus Q of the water equals 0. Okay. Move my picture back. All right. So you can use this relationship here to figure out exactly what's happening with temperature change and energy flow when you're adding something hot to something cold. And it doesn't have to be a piece of metal. It could be 50 milliliters of hot water is added to, 50 milliliters of cold water, something like that. So let's look at an example here. You have a 32.5 gram cube of aluminum initially at 45.8 degrees Celsius. It's submerged into 105.3 grams of water and 14 degrees Celsius. What is the final temperature? I'm telling you, finding the final temperature is going to be the most common that you see for these types of problems. Note, you're given a mass and a temperature for both the aluminum and the water. The water, you should know the specific heat, 4.184 joules. For the aluminum, you can look that up, or it'll be given to you in a problem. And you're assuming, when it says assume the aluminum and water are thermally isolated from everything else, what that means is the system itself is not losing heat to the environment because, I don't know, the lid is off or it's not a tight seal. It just means that you're assuming it's in a vacuum, basically. Okay, so we're going to be finding the final temperature. Remember, the final temperature is going to be the same for both the aluminum and the water. So this is all of our given information. We're finding the final temperature. So we're going to, again, go with the Q of the metal is equal to negative Q of the water. Okay. So let's look at the math. So now that we know this, and this is for the metal, this is for the water, we can go ahead and plug in everything that we have. We can plug in all, our mass, our specific heats, mass, specific heat. We can kind of combine those, right? Clean it up a little bit. And now delta T of the aluminum, we can solve for as being delta T of the aluminum is equal to the negative 14.998 times the delta T of the water. Now, the problem is, what do we know? We know that, hold on, let me go back. We know that the aluminum started at 45.8 and the water started off at 15.4. That's what we know. So what we have to do is we actually have to plug in the initial temperature of the water the initial temperature of the aluminum and then rearrange to solve for T final. Okay, so they've just done the rearranging first here. If you need to, pause this, just take a look at it, try to rearrange it yourself, make sure you know where everything is going and why. And then they finally just plugged in all the pertinent information, plugged and chugged. This is all plugging in everything they needed after rearrangement of the mathematical expression. And they get this, okay? And that is the final temperature for both the aluminum and the water. Again, if you're struggling with the math here, pause, try to work it out yourself and do the rearranging yourself. Basic algebra skills. I'm going to stop this lecture here because we've already gone over this with the one I already uploaded.